All right, in this video, we're going to answer two very common questions in electrochemistry, which are why do voltages of reactions change with pH? Oftentimes they do, not all the time. And why do voltages oftentimes change uh, at a rate of 59 millivolts per decade or per pH unit? And so where this comes from is first the idea of standard conditions, right? And under standard conditions, we write E naught, that's the voltage, the standard reduction potential of a reaction. And remember that this occurs at a certain temperature, 25 C, and that the concentration of all the reactants are 1 molar under standard conditions, right? 1 molar. So if you have a reaction with 1 molar protons in it, okay, well, we know pH equals the negative log of the concentration of protons. And so the log of 1 molar, log of 1 is 0. So when you're talking about an E naught and you have protons in that half reaction, for example, oxygen plus 4 electrons plus 4 protons, we have protons in this reaction, goes to 2 molecules of water, very common oxygen reduction potential. Standard reduction potential for this reaction, if you look it up, is in the table of standard reduction potentials is 1.23 volts positive versus hydrogen, okay, versus SHE. So this is at pH 0. Why? Because, and it's only at pH 0, because there are protons in this reaction. So how do you do this at other pHs? How do you calculate this? Well, you have to use the Nernst equation. Remember, the Nernst equation is what tells you what the voltage is under non-standard conditions. So you have E equals E naught minus RT over NF ln Q. Q is the equilibrium expression. So if we think about some generic reaction like oxidized species with some stoichiometric coefficient, I'll just call it, let's call it Y. Y moles of oxidized species reacts with N moles of electrons and M moles of protons. That goes to, let's call it Z moles of reduced. So if we were to write now this expression for generic voltage in terms of, as a function of the standard reduction potential, we have the ideal gas constant, the absolute temperature, the temperature in Kelvin, the number of electrons transferred in the half reaction, Faraday's constant, and ln, and now for Q, we can sub in the equilibrium expression, which we know is the concentration, or more formally, we should use the activity, okay? That's technically what it is. Activity and concentration are similar, but they're pretty much the activity coefficient, remember, data V coefficient is gamma times the concentration, okay? Usually we call this, assume this activity coefficient is 1. That's a good case for water where you don't have a lot of ion pairing. So then activity and concentration are the same thing, but that's not necessarily true for other solvents. But anyway, that's a little bit of an aside. We can write here the activity, therefore, okay? The activity of what? Of the reactants over the products. That's what, or sorry, the products over the reactants, so reduced species, right? So it's products over reactants. So activity of reduced to the power of Z to the power of their stoichiometric coefficients. And the activity of the oxidized to the power of Y, right? Electrons, that part's already in here, in there for the N, and then we have the activity of protons to the power of M for how many protons are transferred. Now, if you remember with these coefficients, these equilibrium coefficients, you never include solids in the activity coefficients, because solids aren't contributing to the concentration of the species in solution. We're talking about solution here. We're talking about pH, we're talking about liquid electrochemistry. So these reduced and oxidized species, those reactions are occurring on the electrode. They're absorbed on the electrode. And so you kind of treat these like solids. And so for that same reason, we just drop these out of the equilibrium expressions, just like we don't include solids in KSP values. Remember, solubility product constants. So this simplifies to now just ln natural log of A activity of protons to the m power. Okay, well, we can simplify this even further because we know rules here with exponents. So we have 1 over an exponent. This is a negative m, right? So we can pull out a negative m. So this is going to become positive value, put m on the top, mRT over NF times ln, and then this would come to the top, activity of protons. Now what I'm going to do is I'm going to recall the change of base formula. So the change of base formula says that the log of something with a value of the log with a base of A and taking of B is equal to the log of that new base, B, over log of what the old base was, okay? So in our case here, if we're going to write something analogous, what I'm trying to do to change a base here is I want to take advantage of the definition of pH, which is the negative log of the concentration of protons. So if I want to rewrite log of the concentration of protons, right, or activity of protons would be a more formal way of putting this, right, up here. I would have log of log base 10, right? This is log base 10. pH system is logarithmic with a base of 10. Log base 10, the concentration protons is equal to, now I want to go into log base E. Log base E is the same thing as ln, natural log base E of concentration of protons divided by log base E of the old base that I was in, which is 10. So ln of 10. Okay, so another way of saying that is that the ln, because this top log base E is ln of A plus is equal to log base 10, I'm just going to drop the 10 now, of A plus times log of ln, log base E, right? ln of 10. This is a times. Okay? So now we can substitute this in. We get E equals E plus E naught, sorry. E naught plus MRT ln of 10. Sorry, I don't know why I put E here. ln of 10, right? It came from here. ln of 10 over n log activity of protons. All right? And we know that pH is just the negative of this. So if we plug in now for negative of log activity of protons. So if we plug that in, well, now this positive sign will become a negative sign. We'll get MRT over NF ln 10 pH. And this is really your generic formula. Okay. So this shows you that if you have a positive pH and you have protons in the reactant, right? Now all this was done assuming protons in the reactant. Protons in reactant. Right? This proton's in the reactant. Why? Because in the very beginning when we did this, that put, remember it was products over reactant, that put it in the bottom here. this term, the proton term. So if you have protons in the reactant, what's saying to you, if you're at pH 0, all this term is going to go to 0, and your E is just going to be equal to E naught, which we knew, because standard conditions, when you have protons around, is 0. But if you're at a higher pH, you're going to make the E naught, the voltage, more negative. Standard potential, reduction potentials, or the reduction potential is going to be more negative. How much? Well, that depends upon the values of M, N, R, T, and F, right? R and F are constants that never change. T depends on temperature, so that changes. So you can plug this in now for kind of, a normal condition, which is T equals 298 Kelvin, close to room temperature. If we do that, we'll get E equals E naught minus M 8.3415 joules per Kelvin mole times temperature 298 Kelvin times ln 10. This is a 3 here. Okay, I want to keep N generic. This is M, and then I have Faraday's constant, which is 96485 coulombs per mole. And you got to check your units here. Always check your units to make sure that things work out. We have Kelvin and Kelvin, those cancel out. We have moles in the denominator, moles on the denominator, we're dividing, so those cancel out. Then we have joules per coulomb. Well, how does that work? A joule, what is a volt? A volt is, by definition, a joule per coulomb. And so this turns out into volts. So this whole thing is going to get you into volts. And so if we simplify this out and you plug this into a calculator, what you end up getting is 0.059 volts times M over N. Another way of saying that is 59 millivolts M over N. And this is where the 59 millivolts per decade part comes in. Okay? Now notice, that's only 59 millivolts per decade is only true if you have a value of a ratio of protons and electron transfer being equal to 1. So if you have one electron being transferred and one proton being transferred, you have 59 millivolts per decade. If you have 2 electrons transferred and 2 protons transferred, you also have that. But if you have more protons being transferred than electrons being transferred, that value is going to go up, and vice versa if it's going to go down. And so now, and if it's 0 protons transferred, right, you're not going to change at all on pH. The other thing to note that we alluded to before is that this was only with protons in the reactant. If protons were in the product, this would have gone to the top, right? And all that math would have stayed the same, except we wouldn't have had a minus sign. We wouldn't have changed this minus sign to a positive sign here. So the net result is that this would have turned into a positive sign. So so again, this is only true with a minus sign if it's in the reactant. If protons are in the product, then this would be a positive sign, and we get more positive voltage with increasing pH. So you can look at some things now, for example, like if you look at standard reduction potential for oxygen reduction reaction, we said that oxygen going to water is 1.23 volts. So this is just this table standard reduction potential I pulled up. And indeed, that's true. That's for protons. That's at pH 0. Okay, we know now at pH 1, at room temperature, this would shift because there's a 1-to-1 ratio of protons and electrons. It would shift 59 millivolts more negative. And you can see that on this table, actually, they list another special case where they actually write this same reaction, but now under basic conditions. So and it has a different voltage, 0.4 volts. This is now, all they did is they got this expression by adding hydroxide to both sides of the equation, And now you have 1 mole of hydroxide. Well, 1 mole of hydroxide, that's a pOH of 0. That's a pH of 14. Remember, pH plus pOH equals 14. So at pH 14, you have this. And we can explain this, right? Because we know that 14 times 0.059 is we look it up, it's 0.826. And now if we just do 1.23 minus that, we get 0.4. So that's where that came from, okay? It's kind of silly that table standard reduction potential will show it under both conditions because you don't really need that. You can just use the Nernst equation. Another thing we can look at is like the Poiret diagrams, which I have other videos on Poiret diagrams, but a lot of times they'll have these dashed lines that show you where water splitting will happen, okay? And we just calculated this line right here. We know that at pH 14, which is off the charts here, but it's about, you can see it's going to if you extrapolate that out, it'll be to about 0.4 volts, and at pH 0, if you extrapolate that out, that'd be up at 1.23 volts. This one's for the hydrogen evolution reaction. Hydrogen evolution reaction, by definition, at pH 0 is 0, right? That's all these values are versus hydrogen gas formation. So it's exactly 0 to make hydrogen at pH 0. But again, there's a 1-to-1 ratio here of protons and electrons being transferred. So we must have 59 millivolt per decade shift. It must get, because it's in the reactants, 59 millivolts per decade more negative at a higher pH. And you can see that's exactly what happens as we get down to pH 14. We have, that minus 0.8 volt approximately limit here at pH 14. Okay, so I hope that video is helpful. Very important concepts here.